Okay, so let us summarize the concept of electrostatic field. E, vector. Okay, the first scenario we encountered was the case where we had a single point-like charge particle in space which behaves as a source charge, small q, at a point capital Q. Let's say that this is our point capital Q in space. We want to observe the force at point capital P by means of a particle Q naught, which is our test particle at the point capital P, where this distance is RQP vector. Suppose that this particle is fixed in an inertial I reference RF frame, an inertial reference frame. Under these conditions, we know that it's quite simple to calculate the field. So the field is the quantity that gives us the force, the electric force at point capital P, is the quantity E at that point capital P, that multiplied times the test charge Q naught gives us this force. That is, in this specific case, this is nothing but a Colombian type quantity, which is given by 1/4 pi epsilon naught, the source and only the source charge Q divided by RQP, quantity square in the direction U between Q and P, vector quantity. This is our electrostatic field E for a single particle. Then suppose, to complicate the scenario a little bit, and suppose to have, instead of a single particle, suppose to have a set, a known set of discrete charges in space. For example, this could be, this charge is here, this is going to be Q1, a point capital Q1, etc., all the way to a point, let's say, capital QK, we have charge QK, and finally we can go all the way to a capital Qn, we have a Q capital N. All right, so we know this charge distribution, so it's known, is discrete, and all these particles are also fixed in an inertial reference frame. They are nailed at the point where they are located. This point Qk is fixed right there. Under these conditions, if we observe at the point here, capital P, with a test charge Q naught, this distance, we call it R vector QKP, is this distance. In this case, we can use the superposition principle, which allows us to eventually find E at point capital P, the observation point, as the sum for K, which goes from 1 to capital N, of 1/4 pi epsilon naught. Any of the source charges Qk divided by RQKP quantity square, U QKP. Beautiful. This is the case when we have many known discrete particles fixed in the inertial reference frame. We then introduce the concept of continuous charge distributions, and so to do that, we had to define a quantity. For example, we define ρ, the volumetric charge density, at a point capital Q as the derivative of the charge with respect to a volume element calculated at point capital Q, Coulomb over meter cube. Okay, this is for a region capital omega characterized by a ρ at any point capital Q in that region capital omega. By means of this discussion of the introduction of continuous charge distributions, so these are continuous, to distinguish them from these discrete charge distributions here. And these are also known and fixed in an inertial reference frame, as all these other cases here. Okay, under all these conditions, we can map this result here, where the sum from discrete distribution to a continuous distribution, so the sum becomes an integral. So in this case, the electrostatic field E at point capital P is 1 over 4 pi epsilon naught is a constant. Let's take it outside the sign of integral. The sum becomes the integral over the region capital omega where the charge is defined. The charge qk becomes a charge dq. What is a charge dq? A charge dq is nothing but rho of q dv. This is my charge dq. See this definition down here. This quantity has to be divided by r qp, which is the distance between this q and the observation point p, as always in the unit direction qp, uqp. Beautiful. This is for continuous charge distributions. Of course, you can do the same thing in 2D, 1D. So we define also small sigma, and we define also a small lambda. In fact, we give a bunch of examples where we use discrete or continuous charge distributions. One of the most important examples is that of the infinite straight line. Okay, so I remind you that for an infinite straight line with density lambda, which is uniform, in this case, the electrostatic field E is given by lambda over 2 pi epsilon naught r in the radial direction with respect to a coordinate system, cylindrical coordinate system, where this is the z-axis and this is the r-axis, and where phi, of course, is in this direction, is the origin. So that's the expression, very important. We've done this in many different ways, in fact. We look at this with this definition, then eventually with Gauss's theorem, and then eventually we revisited with the rotational property, okay, later on in other videos in the future. Okay, we also have done other examples like the infinite plane, the circular charge, the loop of charge, the charge loop, etc. One last comment which is worth doing here, it's a special case when we do not know, so not known distribution of charges, unknown distributions, and not fixed in an inertial reference frame. These are a problem. Okay, in this case, you cannot use any of whatever is written up here. We had to define an operative definition of E. In this case, the operative definition of E tells us that E at point capital P is the limit for Q naught, the test charge, which goes to 0 plus, of the force at point capital P divided by Q naught. This limit has to be intended in a physical sense, because of course you cannot have anything smaller than an electron. Most importantly, we consider the example of a semi-infinite slab of conducting material, which we will study later in 342. In this case, if we place a lot of positive charge on this surface, we want to make sure that our test charge Q naught, if this is the total charge Q on this plane, has to be much larger than Q naught. So this limit has to be intended in this sense. In that case, the perturbation due to this small charge on the actual distribution of charges is marginal. And that's it.